Okay, so my talk tonight is on a little tool we wrote for testing. How many of you came from another language and were using an XUnit test framework? Have you ever heard of that? So what language were you coming from?
.NET.
Where?
.NET.
NUnit?
Yep.
Maybe JUnits or just Python unit tests, all that good stuff. So I have an addiction, a problem. I don't know how I'm going to get over it. All I know how to write is testing tools on GitHub. Done a lot of them now. First one's for Python. GoConvey is a pretty mildly popular testing tool for Go that we like and have used for a while. ScanTest is another tool in response to GoConvey. I don't know why I did it. That runs your tests automatically for you. And then there's GUnit, this tool I want to talk about today. So just for those that are new to Go, to write a unit test, you just you do the underlying stuff. You have to define a function that starts with test, that receives this testing.t parameter, and then you invoke stuff and check results and call an error function. It's a nice, simple convention. You just define a lot of these functions. You run go test with the command line, and the Go tool just picks them all up and runs them for you and shows the output. It's a simple convention. GUnit introduces more of the XUnit conventions that you may be used to, or may not. So here's a simple example that I'll show in a second. Imagine with me for a second that you're writing the software for a thermostat. And in production, this thermostat software is going to interface or integrate with a real live thermometer that senses the ambient temperature. And then, depending on that temperature, is going to interface with a real live HVAC unit that cools, blows, and heats, and has to do the right thing in order to control an environment. In the test environment, you don't have access to a real thermometer, nor would you even want to deal with that, nor do you have the HVAC unit. So we're going to mock those things. We're going to implement a few structs, say, that have methods on them that satisfy interfaces, say, from a manufacturer of these pieces of hardware. And in this test, we're going to say that the ideal temperature is around 72. We're going
70.
to, yeah.
68.
We're going to create a fake HVAC and a fake thermometer and pass them into our thermostat, which is what we care about testing in this case. We're going to set the current temperature way above the ideal. And what would you expect the HVAC, or what would you expect the thermostat to do with the HVAC in this case?
Turn on the cooler.
Turn on a cooler and hopefully a blower. So after regulating the environment, we're going to do a little check. If our fake HVAC registers as cooling and blowing, we're good. Otherwise, we mark the test as failed. So I'm calling this example ugly. You may not think it's that ugly. It's pretty straightforward. But here's what I define as a really pretty nice test. There's some A's. There's 4 A's of a unit test. Optionally 4. You have to arrange a few things. That's like initializing the fakes and passing them into the thing you're testing. And then you actually have to call the thing that's under test. That's the regulated environment step for us. You have to do an assertion or a check of some sort to see that everything worked well. And in some cases, you have to tear some stuff down. Those are the 4 A's. Arrange, act, assert, and have it. And I'm going to postulate or just say that the ideal test would be composed so that each one of those A's is just on a single statement, a single line. That would be the easiest test to read. And so the ideal maximum vertical length of a test for ease of reading is only 4 lines. How many of you have seen tests that go over 4 lines, just like the last one? Or are, you've probably seen some monsters out there. So let's try and read factors. And see if we can just get it down to 3 statements. Because really there was only an arrange, an act, and an assert. We didn't have an annihilate in that test. So here we go. Let's extract a function, okay, that returns what we need to work with. So initialize the thermostat with a hot environment. That's kind of an awkward name. Comes back to controlling an HVAC. We're going to regulate the environment. That's the act step. We're going to assert that we're cooling and blowing. and we have to pass in the HVAC, because he's the one that knows whether cooling and blowing is happening. And we also have to pass in T, because you have to call T.error if there was a problem. Okay? So that's 3 lines, but I'm not happy with it, because the signatures that results from those extracted functions are a little gnarly. There's the thermostat that you have to pass in, fake HVAC, or excuse me, those are returned, and that's a little bit awkward. Imagine if you proceeded to the next test, which was seeing that the heater kicked on if the temperature was too cold. You're going to have to do these same kind of extractions for that test if you want to obey this single line per step rule that I've proposed here. And passing in testing.t everywhere is going to get annoying really fast. And let's say we have to pass in something else later other than the HVAC to do the assertion. It's going to get messy. And we're not going to be content to do that. We're just going to put everything back in the testing function and call it good. So it's clumsy, it's going to go fast. Here's some wishful thinking. This is what I wish I could be doing. Rather than define a single test function and have to deal with all the scope in that local area, I wish I could define a struct and attach some functions to it that the test tool, the Go test tool, would just pick up for me. So, supposing that this was run by the framework, set up all those fakes and the thermostat, make it hot, regulate the environment, and assert that the cooler's on. I'd love to just be able to say that these functions are void and niladic, meaning they don't return anything and they don't expect anything. They're really simple. It's easy to understand. But the Go test tool isn't going to know what to do with that struct. We're going to have to create some sort of test function that initializes that struct, calls setup, and then calls the test function, and when we have to pass in T, right? Because that's how the testing framework works. So just like the gentleman who talked about the Go generate command, he read that blog, and then 4 months later had an idea, hey, I could use this. I had a similar experience a few weeks ago. What if the boilerplate of initializing that fixture and calling the setup and then calling the test function, this method, what if I could just generate that? Go generate, or just calling the command. So that's what GUnit is. It allows you to adopt a fixture type convention rather than just a function convention, which is what Go expects. And it goes between. It takes your fixture and generates test functions. Here's sort of what it looks like. You'll recognize that directive. It's calling the GUnit command. You create a struct, and you need to embed the GUnit.fixture type. That's the only real requirement that we have here in order for the GUnit command to know what to do. And that's where the testing.t lives. You can still call error. We'll still have that available to you in your fixture. We stick all of our state there. There's a setup function that you saw earlier that's still here. It's just not shown. And here's our test. Okay? Now imagine that this system is getting a little more complex. You find out that after the heater turns off, the blower has to stay on for 5 minutes, or else the heat is going to melt stuff. So you'll need a test for that. You're going to want to make it hot. You're going to regulate the environment a few times to make sure the temperature stabilizes and then the blower stays on, and you're going to have to make an assertion. After the cooler turns off, you can't turn it back on for 5 minutes. So as rules get added, this fixture is a nice abstraction and holds all the state that we ever need, and you never have to pass anything everywhere because you're on a struct with fields. So here's what it looks like from the command line. To work with this tool, you go get it, you go install the code generator, which is nested, GUnit/GUnit. I know that looks weird, but that's correct. Then you call go generate on your package. And you do an ls in your package. And you see your production code, you see your test code, which is where your fixture lives, and then you see this new file, which was generated. And that's actually where the test functions live. That's where T is passed into your fixture. You don't have to worry about that. It's done for you. You probably are wondering what the generated code looks like. Does it really work? Yes, it does. Just pull it down and try it out. There's several examples. I guess I should show you that. Here's an example of a more fleshed out environment controller. And you notice that all of the tests are tiny. They're not because of the abstraction of the struct, there's just not a whole lot to do other than act and assert, because setup has been abstracted for you. There are lots of ways you can code this up. That's just one way. Are there any questions about why we need to do this, or how it works, or anything? Thank you. Happy Death Day.